So now we're getting into the nitty-gritty of momentum, linear momentum. And now what we've seen previously is that whenever there's an adjective, it implies there are other adjectives that could be used. If momentum is momentum, we wouldn't need to add linear momentum unless there's other kinds of momentum, and there are. The most important one for our purposes is angular momentum, and that is we're going to study that at the very end of the course. Angular is, or it's also known as rotational momentum. So the formula for linear momentum is P equals mv. The definition of linear momentum, if you were to ask, if you look it up, you'll find it's just like it's the product of the mass and velocity of a body. So that's the formula. Velocity, mass. If we put in units, mass is measured in kilograms and velocity is meters per second. So the units of momentum are kilogram, meter per second. We could also write it as kgms minus 1. But that's the units of momentum. Now, some people wonder why momentum has a P. Well, there's a long and rich history about momentum. And in preparing this unit, it even occurred to me that maybe I should write a book about the history of momentum because it's such an important, exciting idea. But the word momentum is related to the word impetus. The Latin im plus petera, which means to go to or seek. Oh, so this is movement, to go to seek. How the momentum of something kind of wants to go somewhere, almost like it has purpose. Oh, if a body has momentum, which is the product of mass and velocity, and inertia says that velocity wants to stay the same, then it has a purpose. It has this property in of itself that wants to maintain, that will give it a direction, which will give it guidance. It will allow it to go or seek. Impetera. Greek, petasthai, to fly. Same root as pteron, like Lepidoptera, butterflies. Pterodactyl, flying reptiles, and so forth. To fly. If you are riding your bicycle down the road and you have a basket on the front of it and there is something in the basket and you hit something and come to a stop, well, that object wants to keep going. It will fly out of your basket. If you put something on the roof of your car and gradually speed up, and then you remember that it's there and you slam on the brakes to stop, it will continue. It will fly off the car. So there's a lot of deep connections and richness in the words. Fly, to take wing, to seek, based on some kind of inherent property of its motion, which we call its linear momentum. Now, there's an interesting history, as I alluded to, that momentum was the first time it was correctly articulated was by a devout Muslim, Ibn Sina, also more commonly known as Avicenna, in about 1020 AD. He was actually considered as the most influential thinker of the pre-modern era. What most people don't give credit for in the Renaissance and all of that is all of the, from the golden age of Islam that preceded the Renaissance. Much of the intellectual work and heavy lifting that was done during the Renaissance actually had its beginnings from the Muslim golden era, the golden age, which was inspired by the ancient Greeks and so forth. So Avicenna, who most of you probably never heard of, actually surpassed Aristotle, which everyone has heard of. And by the way, Aristotle had the idea of momentum completely incorrect. Every aspect of it was wrong. During his time, shortly after, there was a fellow, John Philoponus, who got it more correct than Aristotle, much more close to being correct than Aristotle. But even so, even though, Aristotle had his ideas, John Philoponus made corrections to that which are more in keeping with what we understand and much closer to the modern day. For more than 600 years after Avicenna, and more than 1,100 years, the Catholic Church put all its eggs in the basket of Aristotle. And in fact, this is part of the famous disagreement between Galileo and the Catholic Church, because Galileo dared to say that Aristotle was wrong. And the battle was about the Catholic Church saying only the church gets to say who is right or who is wrong. Individuals don't. And so there's a long history of this idea. First discussed and put out by Aristotle, put in a correct direction by John Philoponus, later corrected to its purely true correct form by Avicenna, and still rejected by Galileo 500 or 600 years later. Really, really fascinating history there for what is perhaps the most important idea in all of mechanics and physics. So, momentum, P equals mv. Velocity is a vector, which means it has direction, which means that momentum has a direction. Velocity can be positive or negative. Momentum can be positive or negative. Velocity can be north or south. Momentum can be north or south. Left or right, east or west, and so on. So important things to know about linear momentum. Pretty simple formula, and unfortunately it's one of them that they give us in the AP formula sheet, except it's so simple we don't really need it. So a simple calculation. Let's just do an application. A high school student is about to cross the finish line. Estimate her momentum. Well, we'll start with the formula. P equals mv. All right, well, we need a mass. A mass of a high school student. We're not given it, but we could probably estimate it. Let's see. We go back to our table of masses that we could rely on off the top of our head. And we know a football lineman is 100 kilograms. A loaded backpack is 10 kilograms. So this female runner in high school is going to be somewhere between 10 and 100 kilograms. Maybe half the mass of a lineman. So maybe 50 kilograms. Notice we can get a handle on how large that might be. So 50 kilograms. And then the velocity. Well, wait a minute. All right, so 100 meters. What do we know? The 100 meters, the world record for men is about 9.6 seconds. The world record for women is about 10.5 seconds. Something like that. So let's round it off to about 10 seconds. Except she is going to be slower than that since she is in high school. But let's say it's 10 seconds. All right, so let's see. Well, average velocity is displacement over time. And so we've got 100 meters and 10 seconds. Well, that's going to be an average speed of 10 meters per second. An average me, but we know the initial velocity is 0. And if the average speed is 10 meters per second, then what is the final? She's about to cross the finish line, you see. We can't use this 10 meters per second because finish line, we don't know how fast she's going at the end of this finish line. Now, if we assume that she accelerates evenly the entire time, then we could use this, v plus v0 over 2, and then we would know that she started out with a 0 velocity, then the final velocity might be 2v bar or 20 meters per second. Turns out it's not really reasonable to assume she accelerated the entire time. Most 100-meter runners only accelerate for about the first 40 meters or so. But all of this being said, we know that 20 meters per second would be too fast. 10 meters per second as an average speed would probably be too fast. But if we went with that 10 meters per second, we know we're going to be somewhere close to that. So 50 times 10 is 500 kilogram meters per second. Now the 50, we don't really know, but the uncertainty is probably here. And with this, the uncertainty is probably here. So what we're going to say is really about 5 times 10 to the second kilogram meters per second, which means we don't know if it's 6 or 4. We're saying we're not sure which hundred it is, but it's about 100. Could be 4 times 10 to the second, could be 6 times 10 to the second, could be 5 times 10 to the second. So just doing a simple momentum calculation was too basic as our first calculation. I wanted to throw in an estimate here. But that's how we would use that formula to determine the momentum.